Hello, welcome to today's class on material science. So we are going to be talking about planar packing fraction and planar packing factor. Now, just like the name implies, planar simply means plane. Okay, so what is planar packing fraction? Planar packing fraction is the ratio of the area of the total number of atoms which exist on a plane to the area of the plane itself. So mathematically, planar packing fraction, P fraction, okay, is equal to the area of atoms on a plane to the area of the plane okay. So given a certain plane, all right, so it's just for you to determine the total number of atoms which exist on the plane multiplied by the area of the atoms itself. Of course, area of atom is always the area of a sphere because atoms are spherical in shape. All right, then divide that to the area of the plane. Next up, planar packing factor is simply the ratio of the number of atoms which exist on a given plane to the area of the plane. So mathematically, planar packing factor, PP factor, okay, is equal to the number of atoms on a plane, okay, divided by the area of the plane. All right, so if you're able to compute the number of atoms on a plane divided by the area of the plane, then you have the planar packing factor. So that's the major difference between the two, planar packing fraction and planar packing factor. Now, in the previous video, we talked about crystallographic structures, and there we talked about the simple cubic structure, relationship between the lattice parameter and the radius of an atom. We also talked about the body-centered cubic structure and the face-centered cubic structure. So do well to look over those videos. I will post their links in the description of this video so that you can properly understand. But in that video, I said that the lattice parameter for a simple cubic structure SC relates with the radius in this manner. A is equal to 2 times the radius of the atom. So this becomes the lattice parameter for a simple cubic structure. Whereas for a body-centered cubic structure BCC, we said the lattice parameter A is equal to 4r all over root 3. Okay, this is the relationship between the lattice parameter and the radius of the atom for a body-centered cubic structure. And finally, for the face-centered cubic structure, we had that A is equal to 2r times root 2. So these are the relationship between the lattice parameters and the radius of an atom. So we are going to be using this for this particular video. All right, now let's consider a simple cubic structure. Consider a simple cubic structure. SC stands for simple cubic. Okay, consider a simple cubic structure. So we drew a plane for simple cubic structure. Let's do that again here. All right, in the previous class, but let's do it again here. So for the simple cubic structure, we have the planes in this manner, and we said on each corner we have atoms which exist on each corner of this simple cubic structure. We have atoms which exist on each corner of the simple cubic structure, and we have atoms on each corner of the simple cubic structure. Now, what the planar packing fraction is talking about is pick out a particular plane on this structure. So it can be an FCC, it can be a BCC, but now we're considering an SC. Pick out a particular plane and tell us the total number of atoms on that plane. Also find the area of the atoms on the plane, divide that by the area of the plane. So let me choose this particular plane. Of course, this is a cube, so which means all planes are the same. So if I pick out this particular plane, I will have something like this. Okay, I will have something like this. So this is the particular plane I'm dealing with. Of course, the planes are the same. Now we have corner atoms. We also have corner atoms. We have corner atoms. We also have corner atoms on this plane. Okay, so these planes are what? The same for all. And we showed in the previous video that distance between two corner atoms is called the lattice parameter, which is simply what? A, and that A is equal to 2 times radius for the simple cubic structure, which we already explained here. All right, so that means this is also what? A distance between two corner atoms. There's a corner atom here, there's a corner atom here. Therefore, distance between them, A, is also equal to what? 2r, and that is called the lattice parameter. Therefore, the area of this plane becomes area of the plane, since this is now a square, okay, area of plane is now equal to the length times the width, or we simply say the area of a square, because this is a cubic square. Therefore, we have here the length is 2r multiplied by the width is also 2r. So this implies that the area of the plane, okay, area of plane is simply 2 times 2 is 4. R times R gives us R squared. So this gives us the area of this plane where these atoms are found. Now the next thing to do is to find what? The total number of atoms. In the previous video, when I talked about crystallographic planes, I said that these corner atoms are not actually providing their entire volume or their entire area, as can be seen here. Rather, they are bringing part of their area. Now we've considered this phase. For this phase, we have 1, 2, 3, 4 corner atoms. In the previous video, I explained, when I talked about crystallographic planes, I said on the simple cubic structure we have 1, 2, 3, 4, 5, 6, 7, 8. So since we have total 8 corner atoms, it means that individually this particular corner atom is providing 1/8 of each atom. This is also providing 1/8 of each atom, and the rest of them are providing 1/8 of their atoms. And in general, since we have 8 corner atoms, multiply that by 1/8, it means that for the simple cubic structure, they all combine to produce 1 atom. Now we've considered this phase. On this phase now we have 1, 2, 3, 4 corner atoms. So since we have 4 corner atoms and each of these atoms are not bringing out their full number of atoms on this position, that means this particular atom is bringing 1/4. Since we have 4 corner atoms, it means that this particular atom is bringing 1/4 of its atomic size. This is also bringing 1/4 of its size. This is also bringing 1/4, and this is bringing 1/4. So therefore, the total number of atoms present here becomes number of atoms now. Okay, number of atoms becomes, simply call that n, is now equal to 1/4 times the total number of corner atoms, which you are seeing here, 1, 2, 3, 4. So 1/4 times 4, which is equal to 1. So which means that for the simple cubic structure, these 4 corner atoms combine to what? Provide 1 full atom. And we know that every atoms are spherical in shape. That means the area of an atom becomes the area of a sphere. Therefore, area of atom is area of a sphere. Okay, so the area of the atom becomes the area of a sphere, and since we have only 1 atom, it means we have only 1 area of a sphere. Therefore, the area of the atom, okay, is now equal to the area of a sphere we know is pi r squared. So we simply have this. Okay, so having known this now, we can now find or compute the planar packing fraction. Planar packing fraction is area of the atoms on the plane all over the area of the plane. We found out that the area of this plane is 4r squared. Therefore, planar packing fraction, okay, is equal to area of the atoms. We have just 1 atom, remember, just 1 atom. So that atom is 1, and its area is pi r squared, as we've explained there, all over area of the plane. The area of the plane we obtain here to be what? 4r squared. So we have all over 4r squared. So notice here that, of course, 1 times pi r squared remains pi r squared all over 4r squared. So r squared cancels 4r squared. R squared cancels r squared, sorry. Therefore, we have that the planar packing fraction, okay, planar packing fraction is now equal to pi all over 4. And if we compute pi all over 4, we are going to obtain approximately 0.79. Okay, so this becomes the planar packing fraction for a simple cubic structure. We have that to be 0.79. Whereas if we want to find the planar packing factor, okay, the planar packing factor now is simply the number of atoms which is on the plane divided by the area of the plane. And we've said that for this simple cubic plane, the number of atoms is simply what? 1 atom. We obtain that here as 1 atom. Therefore, the planar packing factor becomes 1 all over the area of the plane, and area of the plane gave us 4r squared, so it becomes 1 all over 4r squared. The unit of this is simply atom per squared meter. So you have this becomes the unit of the planar packing factor, whereas the planar packing fraction is a ratio of area, so it doesn't have a unit. So this is in the case of a simple cubic structure. Now we could have a body center cubic structure, we could have a face center cubic structure, and as the case may be. Okay, so let's now consider a question which could explain the face center cubic structure and the body center cubic structure in general. So please, you're going to keep this in mind. We are going to be we'll keep this particular information in mind, that the relationship between a lattice parameter for SC is 2r, whereas for BCC is 4r all over root 3, and for FCC is 2r root 2. So these are going to guide us in determining any other problems we are going to do over there. So let's pick up a problem and see how it works. All right, so let's say we are given this problem on the board. It says determine the planar packing factor and fraction for the given planes. So you have FCC 110, you have BCC 111. So not forgetting, planar packing fraction or planar packing factor is given as number of atoms, okay, on the plane all over area of the plane, whereas planar packing fraction is given as area of the atoms on the plane all over area of the plane. So let's start with the first case. We'll have FCC 110. So we'll pull it out. Face center cubic structure, the Miller index is 110. So before we start solving this, let's first of all draw the face center cubic structure. Okay, so we have our cubic plane. All right, let's draw the face center cubic structure and see what it looks like. All right, so we have this, we have this, we have this, we have this. So call this my y, call this my x plane. You can choose any direction. Call this my z plane. You still have the same orientation or the same result. All right, remember that each corner atoms or each corner contains atoms. This is the simple cubic structure first. Okay, so for a simple cubic structure, each corner contains an atom, and we have this. So total of 8 atoms, 1 2 3 4 5 6 7 8. So what tells us now that this is a face center cubic structure is, just like the name implies, face center cubic. It means that at each face we have an atom centered at each of the face. So face center cubic. So it means that on this particular face I have an atom centralized. Now this atom is half, whereas on this particular face behind now, which is this particular face inwards, this face behind also produces another half. So both of them combine to produce one full atom. So this face behind also produces a half atom. So we have that these two atoms are what? Sharing to provide a full atom. Then again, on this Z face now, this particular face here, we also have a central atom. Meanwhile, on the Z face behind, we also have another central atom. So both of them combine as well to form what? One full atom. Also on the upper plane we have a central atom. On the directly opposite to the upper plane, which is the lower plane behind, we also have a central atom. Both of them combine to form a full atom. So this is why it's called a face centered cubic. On each of the faces there are central atoms. Now the Miller indices are given as 110. So we need to convert this to plane so that we can draw the plane. Converting the Miller index to plane, remember I said take the reciprocals. So 1 all over 1 gives us the x-intercept, and that's 1. 1 all over 1 here also gives us the y-intercept, which is also 1. And then 1 all over 0 gives us the z-intercept. 1 over 0 is infinity. So these are the z-intercepts. So from the origin, you find your x-intercept is at 1. And these are all unit cells, which means all their sides are the same, 1. So please do well to look up the video on crystallographic planes. I explained all of this on that video. I'll post the link in the description of this video, so do well to look up it so you can properly understand the concept. Okay, but each of these cells or each of these cube now has a unit cell, which means their distances to y, x and z are all 1 meters apart. So x-intercept is at 1, so which means from the origin it intercepts x at 1. Y-intercept is also at 1. From the origin it intercepts y at 1. Alright, z-intercept is infinity, which means this plane, x and y plane, are what? Parallel to the z plane. Now that simply means, first of all, join this plane together, your x and your y, since there is no z. Now since the z is infinity, it means make the z your origin. If you make z your origin, we have y-intercept, or we have x-intercept at 1. So from here to x is also 1. This can also be 1. And y is also 1. From here to y is also 1. This can also be 1. So join y and x together. So it means that these planes are parallel to one another. So you can see the plane. Okay, this is simply what? The plane, and this plane is rectangular in shape. So let's pull out this plane. Okay, this plane is rectangular in shape. We'll have something like this on the plane. Now remember that on each of these plane, on the corners, we have corner atoms. So we have a corner atom here. Also on this corner we have corner atoms. So on each of the corners of the plane we have corner atoms. Okay, and we have corner atoms on each of the corners of the plane. Now if you take a look at this plane now, remember there are body-centered atoms. Okay, on this particular side of the plane, this plane cuts this body-centered atom. So which means we'll have this body-centered atom existing here. All right. Now remember that for a body-centered cubic structure, there is always an atom at the center of each of the face. So if we have picked out one of the face, then which means we must always have an atom at each of these face. And this atom, from what we've explained, is that the atom at one face is pairing with the atom at the other face, from what we explained earlier. So on each of the face, there must be what? A central atom. So on this face, we have a central atom, which means this can also what? On this other face, we also have another central atom. So both of them are sharing. So this brings half and this brings half. Both of them completely combine to give us one full atom. All right. So this becomes the FCC structure for 110 plane. Not forgetting, distance between two atoms we said is called a lattice constant A. But then, what then is this distance? If you take a look at this shape, you have this is now triangular in shape. This is triangular in shape. So which means we can find what this distance, since this becomes a hypotenuse of this triangle. This is now triangular in shape. Distance between two atoms, we call that a lattice constant A. Distance between two atoms, we call that a lattice constant A. Okay, distance between two atoms is also what? A lattice constant A. So which makes this to be what? A. But then, what is this hypotenuse arm, which is the longest side of the rectangle? What is this arm? Simply employing Pythagoras theorem, call here A, call here B, call here C. Then to find AB squared. Okay, I'm just going to do a rough sketch here, because we've done this already in our previous video of crystallographic planes. But AB squared is equal to AC squared. But AC is A, therefore AC squared becomes A all squared plus B squared, and CB squared, CB is actually A, so CB squared is also what? A all squared. This is actually going to give us that AB squared is equal to A squared plus A squared will give us 2A squared. So which means AB, that hypotenuse arm, becomes square root of 2A squared. So A squared, of course, we can find the square root of A squared, but then AB is now equal to square root of A squared becomes A root. Okay, then 2 remains under the root. So it means that this hypotenuse arm is what? A root 2. And therefore, this total distance here from here to this point simply gives us A root 2. So this becomes the sides of the rectangular shape which we've gotten. All right. So having known this now, our first task is to provide the total from the formula, planar packing fraction is simply the area of the atoms all over the area of the plane, while planar packing factor is number of atoms. So we need to find the number of atoms, and we explained that for the simple cubic structure, when there is no body-centered atoms, we have 1, 2, 3, 4 corner atoms here. We have 1, 2, 3, 4 corner atoms. Since we have 4 corner atoms, we said each of these corner atoms are providing 1/4 of their size. This is also providing 1/4 of each size. This is providing 1/4 of each side. This is also providing 1/4 of each side. So which means total number of corner atoms is simply by adding 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4. That simply gives you 1. Or you can simply say, since 1 over 4 appears 4 times, it becomes 1 over 4 times 4. Okay, so number of corner atoms, okay, number of corner atoms is now equal to, it becomes 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4, which we can simply say 1 all over 4 times 4, which is equal to 1. Also, the face-centered atoms, okay, the atoms at each face, would explain that these two atoms are providing, coming together to what? Provide a full atom. So which means these atoms, since they are two in number, that means this is bringing half of its size, and this is also bringing half of its size. Therefore, the total atom at the center becomes 1 over 2 plus 1 over 2. Two of them combine to produce one full atom. Therefore, number of central atom, okay, equals 1 all over 2 times 2, or you can say 1 over 2 plus 1 over 2, which is equal to 1. That means the total atom for the face center cubic structure becomes 1 plus 1. Hence, the total number of atoms, okay, the number of atoms, okay, on the plane N is now equal to the central atom 1 plus the corner atom 1, which is equal to 2. So number of atoms on each plane, on this plane, is equal to 2. So from here, we can find, okay, we'll move on to now calculating the area of the plane. We've gotten the number of atoms. Remember, atoms are spherical in shape. I said that all atoms are spherical in shape. Since they are spherical in shape, it means we can find what? Their area. Their area becomes the area of a sphere. Therefore, area of the atom becomes, area of atom, okay, call this AA, is now equal to, since we have two number of atoms on the face center cubic structure, it means each of them will provide their own area. All right, so that becomes, total area becomes 2 atoms, which will have times the area of sphere, and area of a sphere is pi r squared. So this implies that the area of the atom is equal to 2 pi r squared. This gives us the area of the atom. Now, if we know this as the area of the atom, then let's find the area of the plane. Remember, area of atom on a plane all over area of the plane. So we need to find the area of the plane. This plane is rectangular in shape. Therefore, area of a plane, area of plane, call this AP, is equal to the area of a rectangle, which is the length times the width. So we have length times width, which implies now that area of the plane is equal to, remember, the length is a root 2, so we have a root 2 multiplied by the width remains what? A multiplied by a. This is simply going to give us a times a here, give us a squared root 2. We have this, but not forgetting, we said that for the FCC structure, for FCC, A is equal to 2r root 2. This becomes relationship between the lattice parameter and the radius. So for FCC, A, but for FCC, we said A is equal to 2r root 2. If this is so, then this implies now that the area of the plane is now equal to, in place of a squared, we have 2r root 2 all squared, because this is a squared root 2 and a is 2r root 2, so 2r root 2 all squared times root 2. Okay, this is now equal to, watch now, 2r squared will give us 4r all squared, and then the square root of 2 to the power of 2, 2 cancels the square root, we have it to be times 2, okay, times 2 root 2, okay, simply append your root 2 over there. This implies that the area of the plane is now equal to, so 2 times 4 is 8, we'll have it to be 8r squared root 2. This becomes the area of the plane. So if you know the area of the plane, you know the number of atoms on the plane, and you know the area of atoms on the plane, you can find your atomic packing, you can find your planar packing fraction and planar packing factor. So let's do that over here and see. So let's start with planar packing fraction. Planar packing fraction. Okay, this is equal to, we said, area of atoms on the plane, and the total area of the atoms we obtain that to be 2 pi r squared. That is simply 2 pi r squared all over area of the plane itself, and the area of the plane we had 8r squared root 2. This is 8r squared root 2. So notice now that r squared cancels r squared. 2 goes here is 1, 2 goes into 8 is 4. That means this becomes, at the numerator we have pi all over, at denominator remember we have 4 root 2. Okay, so this implies that the planar packing fraction for that structure is now equal to, pi is 3.142 all over, let's obtain 4 root 2. So 4 root 2 gives us 5.6569. Okay, so 3.142 divides that answer. 3.142 divides answer. This simply implies that the planar packing fraction for that structure is equal to, we have 0.555. So that becomes the answer. Okay, next up we find the planar packing factor, and the planar packing factor is simply the number of atoms. Remember, planar packing factor is number of atoms on the plane all over the area of the plane. Therefore, planar packing factor equals number of atoms on the plane. For this plane, we've obtained that the number of atoms is 2. So you simply have 2 divided by area of the plane, and area of the plane gave us 8r squared root 2. So we have 8r squared root 2. So 2 goes into 2 is 1, 2 goes into 8 is 4. This is now what? 1 all over 4r squared root 2. All right, so you can leave your answer like that. Planar packing factor is equal to 1 all over 4r squared root 2. The unit is atom per meter squared. So you can choose to leave your answer like this, or you can find 4 root 2 and take the inverse, whichever way you're correct. So that is that for the first question, 110 FCC structure. Now let's find 111 BCC structure and see. Now, considering the BCC 111 Miller index plane, BCC 111, okay, so first of all, let's draw the BCC structure and see what it looks like. Okay, once again, we've done all this on our video on crystallographic plane, so do well to look up the video in the description below. I've posted the link in the description for this video. Do well to look it all up for proper understanding. All right, so let me call here my y as always, call here my x, and call here my z. Now on each corner, of course, there are atoms. So this is now, we are starting first with the simple cubic structure. On each corner we have atoms. On each corner we have atoms on each corner. Okay, so what makes this a body-centered cubic structure is simply because at the middle, we said there is now going to be an atom at the center, or at the body of the atom, of the cube, sorry. So there is going to be an atom. So we explained this in our video on crystallographic planes, and I said it's just like you having 8 corner atoms. So 8 atoms resting on one middle atom. So that's what this structure looks like. You have 8 atoms coming in contact with one middle atoms. Okay, that's what it looks like. All right, so now we want to plot the 111 plane. This is the Miller index. So to plot the plane, we've already done Miller indices. Okay, we said take the reciprocals of each of these Miller indices to get the planes. So For the first, the h value, take 1 over 1, you have 1, this becomes intercept on the x. 1 over 1 here, you have 1 intercept on the y. 1 over 1 here, you have 1 intercept on the z. So the plane becomes 1, 1, 1 plane. So let's plot now. Each of them are units. So that means here is 1, here is 1, and here is 1. So from the origin, x is 1, you have it here. From the origin, y is 1, you have it here. From the origin, z is 1, you have it here. So you join all the points together. Okay. This is y to z, y to x, and z to x. So this is the plane 1, 1, 1 structure. So if you pull out this plane, you have an equilateral triangle if you pull out this plane. So not also forgetting that at each of these nodes, we have an atom. At each of the corners, we have an atom. So we have an atom here. We also have an atom here on this corner. We have an atom on this corner. Also, we have a central atom, not forgetting. So there's a central atom as well. Okay, so we'll keep that there. Now, we know that distances between each of these corner atoms is called a lattice parameter or a lattice constant, A. So also from here to here is also called A. Then what then is the hand or this distance of the right angle triangle? So we've done that in the previous example we solved. If here is A and here is A, you can simply compute your Pythagoras theorem to find these points. So from Pythagoras theorem, this becomes the hypotenuse. So if you call here A and call here B, then it means that A, B from Pythagoras theorem, all squared is equal to the sum of the square of the adjacent sides. So the adjacent side you have here to be A, so this becomes A squared plus, you also have here to be A, it becomes A squared, and this is equal to 2A squared. So we agree that AB is equal to the square root of 2A squared, but you can find a square root of A squared, you can't find square root of 2. The root of A squared becomes A, therefore AB becomes A root 2. So that means this arm is simply A root 2 and all the arms are the same. So this is A root 2, this is A root 2, and this is also A root 2. All right, now this is triangular in shape. We need to first of all find the number of atoms. Is a very key term, number of atoms on the plane. How do we find the number of atoms on the plane? We know that all atoms are what? Spherical, which means they make a complete cycle. And the angle on a cycle is simply what? 360 degrees. That becomes the total angle on a cycle. But take a look at these corner atoms now. These atoms are actually acting at what? The angles of an equilateral triangle. And an equilateral triangle have equal angles, and each angle is what? 60 degrees all through. So the angle here is 60 degrees, angle here is 60 degrees, same thing here, 60 degrees. So if this is 60 degrees, that means this particular corner atom is providing 60 degrees of its angle of the entire structure. And the entire atom has what? 360 degrees, but it is providing what? Only 60 degrees. So that means we can find the number of this atom provided by this space. Okay, the number of atoms on this space becomes 60 degrees all over 360 degrees. That becomes the number of atoms provided on this corner. It is also the same number of atoms provided on this corner. It is also the same number of atoms provided on this corner. And 60 over 360 will give us 1 all over 6. So it means that each of these atoms are providing 1 all over 6 of their size. This atom is also providing 1 all over 6 of their size. And this atom is also providing 1 all over 6 of each side on this structure. So in general or in total, the total number of corner atoms is now equal to 16 plus 16 plus 16, and that is simply 1 all over 2, or you can simply say 1 over 6. Since there are 3 numbers, 1, 2, 3, it becomes 1 all over 6 times 3. Number of corner atoms, okay, is now equal to 1 divided by 2. So this becomes, that means these 3 corner atoms combine together to provide half of what? An atom. But it doesn't end there. Like I said earlier, in the body center cubic, we have all the atoms sharing from where? The central atom. So which means these three atoms are sharing from this central atom, and that means that this atom cannot give out completely its size. They are all sharing. Therefore, central atom, okay, number of central atom now, okay, becomes 1, okay, becomes 3, because we have 3 corner atoms which are sharing from these central atoms. So it becomes 3 times 1 all over 2. So each of them are sharing what? Half. So the central atom is giving out some portion, like half of it to each of these faces, half of it to each of these faces. So therefore, this central atom is giving out half of its face to where? 1, 2, 3 corner atoms. So this becomes 1 all over 3 corner atoms multiplied by 1 all over 2, which is actually what? 1.5. So we have this to be 1.5. Hence, the total number of atoms in this structure, total number of atoms, okay, total number of atoms becomes the number of the corner atoms plus the number of the central atom. That becomes half plus 1.5. So you have 1 all over 2 plus 1.5, and this simply means that total number of atoms present there becomes what? 2. So you have number of atoms to be 2. Okay, so we've gotten the number of atoms. Next now is to find, if we know the number of atoms, we can now find the area of the atoms on the plane. And all atoms are spherical in shape, which means they have the area of a sphere, like I said. Therefore, total area of atom becomes, since we have 2 atoms, each of these atoms will contribute their sphere. It becomes now 2 times area of a sphere, which is pi r squared. Therefore, area of atom, okay, is now equal to 2 pi r squared. We have this. All right, so from the formula again, we compute what? Area of the plane. This plane is triangular in shape, which means we need to find the area of this plane. Okay, so area of a plane, okay, area of the plane, call this A subscript P, is equal to what? Half base times height, because it is triangular in shape. So the area of the plane becomes half base times height, which means we need to find the height of this triangle. And if we bisect this into 2, it means that we've divided this base into 2. So we can find here and we can find here. The right angle triangle becomes, now we have something like this. Okay, this side remains a root 2, this side remains a root 2. This is now the height we are looking for. Remember now, upon this bisection, I've divided this side into 2. So it becomes a root 2 divided by 2. So it means that the base is actually a root 2 all over 2. So if we have this, then we can now compute the height using Pythagoras theorem. And from Pythagoras theorem, the square of the hypotenuse arm is equal to the sum of the square of the both adjacent sides. So I will simply have a root 2 all squared is equal to the sum of the square of the both adjacent sides. I have here h all squared plus, also from here I have a root 2 all over 2 all squared. Okay, so from here now, a squared, of course, is a squared. Root 2 squared, the squared cancels the square root, so I'm left with 2. So this becomes 2a squared, and this is equal to h squared plus, same thing happens here, a squared becomes a squared, root 2 squared, the squared cancels root 2. I have here 2a all squared all over, not forgetting 2 squared here becomes what? 4. All right, so this can be written as 2a squared plus h squared equal to, okay, sorry, equal to h squared plus, from here 2 goes into 4, 2 goes into 2 is 1, okay, 2 goes into 4 is 2, so I'm left with a squared all over 2. In order to make h subject, I will first of all send plus a squared over 2 over to this side of the equation. Positive sign cross and equal to sign becomes negative. So I have here 2a squared. This comes here now becomes minus a squared all over 2, and this is equal to my h squared. So 2a squared minus a squared over 2 will give me 3a squared all over 2. This is equal to h squared. So I will now find h by taking the square root of what? Both sides. This implies now that h itself is now, okay, let me take it up a bit. All right, so this implies that h squared, or h itself, is now the square root of 3a squared all over 2, and of course a squared can have a square root. The square root of a squared becomes a, so a comes out. This becomes a root 3 all over 2, and 3 over 2 is 1.5. This actually becomes a root 1.5. So all we need to do now is compute the value of root 1.5. This implies that the height is now equal to, let's find out root 1.5. So root 1.5 gives us 1.22, then we'll append our a to it, so it becomes 1.22a. So this becomes the height of this plane. If that becomes the height of the plane, then we can compute the area now. This implies that area of plane, okay, we said is half base times height. So this is equal to half the base itself. We've obtained the base here as a root 2 all over 2. So this becomes a root 2 all over 2 multiplied by the height. The height we've just obtained now is 1.22a. So multiply by 1.22a. Okay, so I think I can take this off. Alright, so area of plane is now equal to, so let's obtain this multiple together. 1.22 multiplied by, okay, multiplies everything here. Remember, a times a is a squared, so we have here 1.22 a squared root 2 all over, same thing here, 2 times 2 here becomes 4. So let's obtain 1.22 times root 2. So that value gives us 1.73, remember, a squared all over 4. So let's find out now 1.73 divided by 4. So this implies that area of plane is equal to 1.73 divided by 4 gives us 0.433 a all squared. So this becomes the area of the plane. Now we know the area of the plane, we know the area of the atom, we also know the number of atoms. We can now find the planar packing fraction. Planar packing fraction, planar packing fraction, okay, from formula we said it is the area of the atoms, total area of the atom, and area of the atom was given as, okay, we obtained area of atom to be 2 pi r squared. So this becomes 2 pi r squared all over, then we said area of plane all over area of the plane, and the plane itself is 0.433 a squared. But not forgetting, recall we said earlier, okay, that for a body center cubic structure, it is here a is equal to 4r all over root 3. That means a equals 4r, okay, 4r divided by root 3. We said a is equal to this. So this simply means that the area of the plane, which we obtain as 0.433 a squared, can be rewritten as, okay, let's do that over here. All right, so the area of plane, which we call AP, is now equal to, we obtain 0.433 a squared, which is 0.433, but a itself is given as 4r all over root 3 for body center cubic structure. So we append that there, it becomes 4r all over root 3. But remember, it is 0.433 a squared. So we have to square that term. Therefore, area of plane is now equal to, this is 0.433, okay, multiply now by, take note, 4 squared becomes 16. This is 16 arrow squared. So we have arrow squared all over. Take note now, the square root 3 to the power of 2. 2 cancels what? The square root itself. So we are left with 3 here. This is now equal to, so we compute 0.433 multiplied by 16. Okay, that gives us 6.928 r squared all over 3. So let's find 6.928 divided by 3. So this now implies that the area of the plane itself is equal to 2.31 r squared. So this becomes the area of the plane in terms of radius. So it means that planar packing fraction, okay, we can rewrite this now as planar packing fraction, okay, is now equal to, this becomes 2 pi r squared all over area of plane. Okay, we have it here to be 0.433 squared, and we'll obtain the real area of the plane in terms of radius now, which is this. So it becomes it becomes 2.31 r all squared. So from here, r squared cancels r squared. You're simply left with 2 pi all over 2.31. Okay, so pi is 3.142. Let's compute 2 times 3.142 divides 2.31. All right, so that gives us planar packing fraction to be equal to 2.72. We have 2.72. So this becomes the value of the planar packing fraction for that given structure. Next, we compute the planar packing factor, which is simply the number of atoms divided by the area of the plane. So I can do that here. All right, so planar packing factor is now number of atoms, and we obtain number of atoms here to be equal to what? 2. Total number of atoms is 2. So this will give us 2 all over area of plane. So you can choose to use here 0.433 a squared, or you can still choose to use 2.31 r squared. But let me use in terms of the radius. This becomes all over 2.31 r squared. So you can leave your answer like this. The unit is atom per meter squared. So you can choose to leave your answer like this, or you can choose to divide 2 by 2.31, whichever, you still have the answer. So that becomes the answer to that given question. All right, guys, I hope you find this video very interesting and helpful. If you do, I would like to get your thoughts in the comment section. And of course, if you're new to the channel, do well to also like, share, comment, and of course, subscribe to the channel. I will see you in the next video. Thanks and cheers.